Here I'm going to talk about how to ensure code stays easy to maintain. This can be done with a particular discipline of writing tests. Let's start by looking at this entry point. As you can see, this entry point allocates the class responsible for dependency injection, forwards along the command line arguments, and runs the program. Notice that it does not know anything about the business logic. All we can tell by looking at this class is that we are dealing with a command line application. This means that this class never has a reason to change, so it is one of the few kinds of classes where it is okay to rely on a manual test rather than an automated test. We would have to manually check if the application could be launched from the command line anyways, and we only need automated tests for anything that could possibly break. As this class knows nothing about the business logic, it has no reason to ever change, so testing it a single time is enough. It is important to note that we must not have more than one entry point. If we did, it would mean the code for choosing among the entry points is outside of our application, where it is hard to test. In this situation, you would want to re-architect the code into separately tested applications, or refactor the dispatching logic into the portion of your code under test coverage. Now let's have a look at our dependency injection class. Here we are assigning the production implementations for everything we don't control, such as the clock, the file system, and the console output. Dependency injection is one of the few times where I don't rely on any type inference that the programming language might support, as I want to be sure that all allocated classes are only aware of their collaborators by their contracts. This prevents me from accidentally making a class aware of the implementation details of its collaborators. Here there is no logic, and the type system is ensuring each class is hooked up to collaborators implementing the proper contracts. So I don't need to test for this because the compiler is adequate for the job. Now we get into the application behavior. There are only 4 kinds of things to test here. I will call them invocation, environment, side effects, and computation. Invocation is when we were launched from some outside container, such as a web server, or in the case of a console application like this, it is the operating system that invokes us. The environment entails what we can ask of the thing that launched us. In this case, we can ask the clock what time it is, and the file system what bytes are in a particular file. Side effects are commands we send to something external. In this case, we are emitting lines to a console. And computation is the deterministic rules of the programming language. Here we are computing a duration and composing a string. Let's look at what it takes to get this under test coverage. Since all of my collaborators were behind contracts, it is easy for me to create stubs for testing that implement those same contracts. This discipline of designing code in this manner is what gives me sufficient control to make testing trivially easy. For invocation, I just simulate any command line arguments I want, as you see here on line 8. For environment, I create stub classes for the clock and file system, lines 9 and 10, and I am able to fully specify how I want them to behave for the purposes of this test. For side effects, I also create a stub class on line 11. Because I control this stub, I can make it record what side effects would have been sent and ask what those were on line 20. And finally, I can see from looking at the test that the computations were performed correctly. From line 9, I see the milliseconds were 1000 the first time the clock was checked and 1789 the second time. This makes it obvious why line 21 reads 789 milliseconds, and I can do this math in my head. The 2 primary ways to write a test incorrectly are to refactor something away that should be there and to put something in there that should not be there. For example, if I refactored out the values for the clock stub into the clock stub itself, I would not be able to tell by looking at this test if the lines emitted on line 21 were correct. Alternatively, if I was dealing with composing path objects or using a char set to convert a string to bytes, it would confuse this test with details that are outside the concern of this test. My stub for testing the system clock allows me to specify what the clock will say each time I read it. Here I am using mutable state to keep track of which value I want to read next. The nice thing about stubs is that they can be written specifically for the needs of my test. For different tests, I could have a clock that always returns the same time, or a clock that incremented the time by a fixed amount each time it was read. Also notice that I have parameterized the values for the clock. The stub handles the logic for incrementing the next value to read, but it lets the test deal with what values will be used. The most important part and hardest part of designing a stub is deciding what belongs in the stub and what belongs in the test. To help design this, I sometimes start with my stubs as inner classes of the test that needs them and only refactor it out into its own class once I realize the same behavior is needed in a different test as well. My stub for testing the file system associates a file name with the contents of that file. Notice here that I am handling the conversion to a path, the char set, and the conversion from a string to bytes in the stub rather than in the test. This allows the test to be focused on only what is relevant to understanding the test, leaving the implementation details for the stub to deal with. Controlling the design of my stub has also allowed me to be more descriptive in my error message should the implementation attempt to read a path I did not expect it to. The console stub keeps track of side effects rather than applying them. Here, instead of emitting a string to a console, I append the string to an array buffer that the test can inspect later. For more complicated cases than this, I will sometimes create a class to hold all the parameters for an invocation and record a list of this class in the stub. So notice that the 4 types of things to test, invocation, environment, side effects, and computation, were not only easy to test, they were trivially easy to test. It is important to note that there are no other types of things a computer can do. This is all there is. It is a law of nature. Once you figure out how to test these 4 things, you can test anything. By designing the code so that these types of behavior are kept separate from each other, with the non-deterministic parts behind contracts, it can never be the case that code is hard to test. So whenever you think you are looking at code that is hard to test, what is really happening is that you are looking at code that is badly designed. Use tests as your warning system for detecting badly designed code, and remember that you control design. Even if the obnoxious part is embedded in code you don't control, you can use the appropriate language constructs and patterns, such as putting the offending code behind a contract and delegating via the adapter pattern, to bring all of the code you have access to under control. Now we are going to have a look at some other styles of testing. Consider the idea of separating what is relevant to understanding the test from everything else. If you push that idea to its logical extreme, you will end up with something like this. Here I have a tester class that takes care of all the setup, only letting the individual tests specify what values to use. This is useful if you have a lot of tests where the majority of setup code is duplicate and only a few specific things change from test to test. Note that a new tester object is allocated for every test. This is important to ensure that no test can interfere with another, as they have separate instances of all their test data. The potential for test collision is why I would never use a setup or teardown phase, even if the test framework encouraged that style. Even for something like database integration tests, I would move the test database setup to the build system, such as the Maven pre-integration test lifecycle phase, and run each test in its own transaction. Here we have a test that is using a mocking framework. Mocks have the advantage that you are no longer required to create stubs, but as a consequence of this, your test has to specify the behavior of your collaborators entirely. Mocks also more explicitly expose your implementation details to your tests, meaning that even when your change did not affect external behavior, you will still have to update the test if any of the collaborator calls are different. It is harder to refactor duplication out of your mocks than it is for stubs, and while you have complete control of how you implement your stubs, mocks are generically generated as a record playback tool. For these reasons, I would never personally use mocks. I would much rather retain the ability to refactor that I get from stubs. So what do you do when you have to deal with a third-party library that was not written in a manner that is easy to test? Well, I'm going to show that off right now. So as an example, let's look at the files Java class. It has a static method called readAllBytes, which is doing I/O with the file system. So how do you get that under test coverage? Well, one thing you can do is, like I did here, I create a contract class that puts this behind an interface. So I look over here at my files contract, I look at readAllBytes, and here we can see I've defined the signature that, taking a path, returns an array of bytes. You'll note the same exact signature here. So then this is my interface, or in Scala it's called a trait of files contract. Then I can actually create a delegate, and what this does, if you look at readAllBytes, This just delegates straight to the files static method. So now we've effectively put read all bytes behind an interface. Now, when I'm stubbing this out, I can create this other class called files not implemented, and that extends files contract. So let's look what that does with read all bytes. And you can see here it just throws a not implemented exception. So in this way, we have created a files contract, files delegate, files not implemented. So in this way, it's very easy to create stubs. And this is also useful, like if, say, a new file comes, a new method comes out in, say, a new version of Java, and you don't want to have to write all your tests. Well, because all your stubs have extended files not implemented, you just have to change this one class here, and you don't have to go change all those stubs. So one minor thing to note with this style is I always put the contract classes for production in a separate module under main, and then I put the parts for the test also under main, not under test. That just allows me to pull them in through Maven conveniently. So this file's not implemented, you'll see here, is actually in a separate module and it's not under test. And that's just because of how Maven packaging sometimes won't package up your test things. So it's very hard to depend on things that are in the test area of a Maven project. Now I'm going to show off a more complicated example. So here we have an HTTP servlet response in Java. That's a class that we can extend, and I just extend it with a not implemented version for stubbing. So what I want to do in my test is I want to be able to stub it out, and I want to see what was written to the servlet response. So I go ahead and for the stub, I just add this what was written function. But then I realize to figure that out, I got to get access to this output stream here, which is a servlet output stream. So what do I do about that? Well, I just assume what I need already exists. I just create a servlet output stream stub. So again, I go another level deep. We got this servlet output stream not implemented, extend servlet output stream, like so. And then when I finally get to the servlet output stream stub, I create a char set, I create a byte array output stream, and I override the write function so that it captures these to the byte array output stream. Then when I ask it what was written, I can ask the byte array output stream, we'll get your byte array, and then go ahead and convert it to a string with this char set. Again, this is for test purposes. So going back to the response stub, we can see this servlet output stream stub has a what was written, and it just delegates from it, so it's delegating to the servlet output stream stub. If you've designed your code to separate out everything you don't control, as I have shown here, you don't need end-to-end tests anymore. End-to-end tests are much slower, especially in their startup cost, and since they are not testing one part of the code at a time, it takes a lot more of them to get the same test coverage. They also do not put any pressure on the internal design of your code, since they only give you feedback at the ends. This can give you a false impression that the code design was test-driven, but an end-to-end test does not count because it does not put any pressure on your internal design. In this sense, they are the opposite of mocks. Mocks put too much pressure on your design, to the point of verifying irrelevant details. End-to-end tests put too little pressure on your design, allowing you to get away with code that works but is hard to maintain. Your tests have to do three things: fail if the code is broken, not fail if the code is not broken, and provide timely feedback. I would go so far as to say that if you think you need an end-to-end test to achieve this, your code is badly designed. Think about what types of tests you need to have full coverage. For failures on the inside of your application, use the techniques shown here. For failures outside of your application, rely on health checks. For failures at the boundary, use an integration test. For failures launching the application, use a smoke test. A simple smoke test could be to run every health check on application launch. This covers everything. There is no other place that a bug could be that requires an end-to-end test to detect it. To summarize, there are only 4 types of things a computer program can do, and these are all trivially easy to test. They are invocation, environment, side effects, and computation. You want your tests to have all the relevant detail to understanding them nearby and not refactored out to a separate file. You want to move any details not relevant to understanding the test elsewhere. And finally, there is no such thing as code that is hard to test. There's only code that is badly designed, and you control the design of the code.